Hey guys, for the first of two example problems I covered in this chapter, we are told that the moon takes 27.32 days to travel once around the Earth. And the question is asking us to find through what angle on the sky will the moon move in 1 day and in 1 hour. So to help us think about this problem, I drew a picture. So here is the Earth, here is the orbit of the moon, and I am going to assume that the moon's orbit is a circle in this problem. Now, it is true that the moon's orbit is actually elliptical, it is not a circle, but for the context of this problem and what we're doing, a circle is going to be good enough to get an approximation for the behavior of this. So let's suppose that at some point in time, the moon is right here in its orbit. So there's the moon, and we go outside, we're standing on the Earth right here. So here's us on the Earth. And we look out and we see the moon right there in the sky. Now, it takes a little over 27 days for the moon to go all the way around once. So in 1 day, the moon will travel, let's say, this far along in its orbit. So the next night, I go out at the exact same time and I see the moon up here in the sky. So I could say that the moon moved by some angle in the sky, and I'm going to call this angle theta. So through what angle did the moon move in the sky? I look at this picture and I notice that we drew the moon's orbit as a circle, and I know one circle is 360 degrees around. So instead of thinking of this as one orbit takes 27.32 days, I could think of this as saying it takes 27.32 days for the moon to travel 360 degrees on the sky. Now, so if I think of one orbit as 360 degrees, now I could set up a ratio. I could say 360 degrees in 27.32 days is equal to how many degrees in 1 day. So at this point, I set up a ratio. If I want, I could cross multiply, or I could just bring the day to the other side, however you want to solve the math of this problem, to find the angle that the moon travels through in 1 day. So I'm going to multiply both sides of this problem by 1 day. So if I multiply the left side by 1 day, I multiply the right side by the same thing. So now these terms will cancel on the right-hand side. All I'm left with on the right-hand side is the unknown number of degrees. On the left-hand side, the unit of day will cancel the unit of day right over there. And so I could say 1 times 360, there's 1, there's 360, degree over 27.32. And if I put this in a calculator, 360 divided by 27.32 becomes 13.18. So the moon travels 13.18 degree in 1 day. So this is the angle the moon moves in its orbit in 1 day. So I could say this angle that the moon moved in the sky is 13.18 degrees. Now, part 2 of this problem asks us through what angle does the moon move in 1 hour? So the way I'm going to think about this question is from here to here, from 1 day to the next day is 24 hours. So I'm just going to subdivide all this into 1 hour segments, and there's 24 of these in total. So if the moon moves 13.18 degrees in 24 hours, the moon will have to move 13.18 over 24. This will be the number of degrees the moon moves in 1 hour. I'm just taking this total angle and dividing it into 24 equal segments. So I put that in a calculator and I get 0.55 1.5 degrees. So every hour, the moon moves about half a degree on the sky because the moon moves about half a degree through its orbit. So this is the answer we are going with for this problem. Now, I did make some approximations in this problem. We assume that the moon's orbit is a circle and not an ellipse. If you're moving in an elliptical orbit, sometimes you'll be moving faster, sometimes you'll be moving slower, but the moon's orbit is approximately a circle. Also, if we wanted to be more precise, we would have to take into account the fact that the Earth rotates, but I didn't really want to do that because that would be one more layer of complication on this problem. For the next example problem we're going to go through, we are told that the distance to the moon is 3.84 times 10 to the 8 meters, and we are going to assume that we take a very high quality research grade telescope. We use that telescope to look at the moon, and we want to ask what is the smallest level of detail we could resolve with this telescope. So to make an analogy with what this problem is saying, if you think about, you take a picture with a digital camera. You take your picture, you like that picture, you zoom in on that picture, and at some point the picture gets blurry. And the reason the picture becomes blurry at a certain level of magnification is you are now beginning to see the individual pixels that that camera was able to resolve. That camera cannot resolve detail to an arbitrary amount of precision. Astronomy behaves the same way. Due to the color of light that we look with, in other words, the wavelength, due to the size of the telescope, there is a limit to which detail we can resolve with the telescope. And we're basically asking, what would be the size of a pixel if we are looking with a really great telescope at an object at the distance of a moon? So, okay, I could say the moon is 3.84 times 10 to the 8 meters away from my telescope. So here is my telescope. This is the smallest level of detail that I can resolve on the moon. Now, in reality, the moon is about 2,000 miles across. And so this object here looks to be like almost 500-600 miles across. This is much bigger than what I could actually do. But to actually draw that, it would just be an ugly picture on the whiteboard, so I'm just exaggerating this picture. So here is the smallest level of detail I can see with my telescope. And we are told that this smallest level of detail, the angle it takes up on the telescope, is about 1 arcsecond. So this is my angle of smallest detail. And the telescope on Earth is about 3.84 times 10 to the 8 meters away, the distance from the Earth to the moon. Now, you might ask, well, could we put a telescope up in space? Technically, yes, but it's not going to be significantly closer to the moon. For context, I'm going to write this number out just not in scientific notation. So the distance from the Earth to the moon on average, I could write as 384, 1, 2, 3, 4, 5, 6. So this is the number of meters to the moon with all the digits written in. Now, if you are up in space, you might be 100 kilometers up. Let's be generous. Let's say you're 1,000 kilometers up. That's higher than the International Space Station. So if you are 1,000 kilometers up, there is you are less than 1% closer to the moon. So you're not really changing anything by putting a telescope up into space. If you want to significantly put a telescope closer to the moon, you might as well just go to the moon at that point. So, what is the size of this object? So to find this out, we're going to use the small angle formula with theta over 2.06 times 10 to the 5 is equal to the diameter of the object I'm looking at over the distance. Now the distance between the telescope and the moon is this number given right here, and the angular size of the object I am looking at must be written in arcseconds. In this problem, it's already given to us in arcseconds. Hypothetically, for a different problem, if we were given something in degrees or arc minutes, we would need to convert that number into arcseconds. So for the left-hand side of this problem, I could say 1 arcsecond over 2.06 times 10 to the 5 is equal to, now here diameter just means the linear size of the object I'm looking at. So in this case, the linear size of 1 pixel will be this distance right here. So this is my diameter of the object I'm looking at. And then the distance, as I said, is the Earth-Moon distance. So we could say diameter over 3.84 times 10 to the 8. Now, at this point, if I want to, I could cross multiply to solve for the diameter of that object. Another way I could think about this problem is if I multiply both sides by this 3.84 number, I'll be left with diameter just by itself. So at this point, it doesn't really matter how you solve the math of the problem, as long as you go slow and understand what you're doing. So I am going to multiply both sides by 3.84 times 10 to the 8. Multiply this side also by 3.84 times 10 to the 8. When I multiply, this term ends up canceling on the right-hand side. So what I'm left with is diameter on the right-hand side. On the left-hand side, I end up with 3.84 times 10 to the 8 times 1 over 2.06 times 10 to the 5. So I have 3.84 times 10 to the 8 times 1 for my 1 arcsecond over 2.06 times 10 to the 5. And at this point, I'm going to put everything in a calculator, and I get the diameter of the object is 1,864 meters. So, for context, for a problem like this, a telescope that could see an object as small as 1 arcsecond is very good. The Hubble Space Telescope, for example, could see objects down to an angular size. I think it's of about half an arcsecond. And so if you could have half the resolving power of Hubble, that's pretty good for a telescope. Now, a telescope that could see 1 arcsecond size object in angular size could only resolve something that's about a mile across. So 1 mile is about the size of a pixel with this telescope we're using. So the landers, the stuff left behind by the Apollo moon landings were definitely much, much smaller than a mile across, because when you're going into space, the size of the objects you're launching matters. And so this is why we cannot use a telescope, even a very strong telescope, to see the landers and the modules left behind on the moon. For context, 1864 meters, this is also equal to 1.864 kilometers. I could say that a kilometer is a larger measure than a meter, so I would expect the number of kilometers from one side to the other to be a smaller number. That's why I divided by 1,000. Or if you want, you could go through the conversion entirely on your own.